To week 2 of the lecture series on logic design, CMP223. In the last class we looked at logic gates excuse me, and Boolean algebra, where we talked about basic logic gates. We also look at logic gate combinations. We saw truth table, logic gate symbols, and then we introduced Boolean algebra. In today's class, which is going to be the week 2, we are going to continue the class with by looking at Boolean algebra and simplification. So we'll begin with looking at basic basic identities, simplifications using Boolean identities. We'll look at the concept of sum of product form, SOP, product of sum form, POS, and then we'll look at the standard forms of SOP and POS, right? So without wasting much of our time, let's begin today's class. So in the first, remember in the last class we looked at what basic logic gates are, right? We defined what logic gates are. Remember we said that the basic building blocks of digital electronics, and then we examined some of the fundamental, or what we refer to as the primary or the basic logic gates, the likes of AND, the AND gate, the OR gate, and then the inverter. Remember we also established that for the AND gate, for the AND gate to be high, in other words, for the AND gate to be 1 at the output, all the input combinations must be high or must be 1. And then for the OR gate, we said that the rule for it to be high or 1 at the output, at least one of the input entries must be 1. And then the role or the function of the inverter is to change a bit given at its at the input, right? So if it has a 1, it will change it to 0. If there's a 0, it changes to 1. So these are some of the things that we're able to look at in the last class, right? And then there are combinations. For instance, when you join the NOR gate with the AND gate, you have what is referred to as the NAND gate. Similarly, if you join the NOR gate with the OR gate, you have what is referred to as the NOR gate. And from the NAND gate and the NOR gate can be referred to as what is referred to as universal gates, right? So part of the exercise or the take home that we've given us, find out the reason why those gates are referred to as universal gates. So let's begin today's class by looking at basic Boolean identities that has been postulated by George Boole, that was named after him, right? The Boolean algebra, so referred to as Boolean identities. So so we have roughly up to about 21 of those identities or laws, right? So we are going to be seeing some of their provings, some of their proofs using the truth table as a tool, right? So the first one has to do with x plus 0 is equal to x. We are going to be seeing some of the provings using truth table. And then the second one has to do with x dot 0 is equal to or equivalent to 0. X plus 1 is equal to 1. Number 3. Number 4 is x dot 1 is equal to x. Number 5, x plus x is equal to x. Number 6, x dot x is equal to x. Number 7, x plus x prime, which can also be represented as x plus x bar, is equal to 1. And then number 8, we have x dot x bar is equal to 0. 9, x plus y is also equal to y plus x. So the order is not does not matter, right? So in number 10, you have xy is equal to yx. In number 11, we have x plus open bracket y plus z is equivalent or is equal to x plus y, close your bracket, plus z. At number 12, x into bracket yz is equal to xy z. 13, x into bracket y plus z is equal to xy plus xz. Number 14, x plus yz is equal to x plus y in bracket x plus z. 15 w plus x in bracket y plus z is equal to wy plus wz plus xy plus xz. Number 16, excuse me. Number 16, x plus xy is equal to x. Number 17, x plus x prime y is equal to x plus y. Number 18, x prime plus xy is equal to x prime plus y. Number 19, x plus y all bracket prime is equal to x prime y prime. Number 20, xy all prime is equal to x prime plus y prime. And then at number 21, we have that x prime close bracket prime is equal to x. Right, so basically these are some of the basic Boolean identities. So let's see how we can examine some of them. Let's try to prove some of them, and then before we go ahead and then use some of those identities to see how we can simplify those expressions. Remember, as part of the simplification techniques, so we are going to begin with simplifying using Boolean identities, and then in the next coming week we are going to introduce you to K-map, Maurice Karnoff, what is referred to as the Karnoff map. We're going to see some of the simplification technique using Karnoff map, and then in the following week we are going to also look at the Queen MC-Kloski algorithm, which is also referred to as the tabular method. Right, so for this week's just to introduce you to some of the basic identities, and then how you can use some of these identities to simplify logical expressions. Right, so let's see some of those provings using truth table as a tool. Right, so in order to show you how some of these things can be, we can look at let me pick number 9, and then I think number 20 to show you how this can be done using the truth table. Right, so let's quickly jump to our board and try to prove this. See, okay, so what we have, assuming we have x, we are going to be solving two problems actually from those laws. One of it has to do with x plus y, that is the identity, identity at number 9 that said x plus y is equal to y plus x, and then number 20 that said xy. I think okay, let's just copy the two of them so that we know the two we'll be looking at. So the second one has to do with the xy all prime is equal to the individual x prime then plus y prime. So these are some of the two examples we are going to be looking at to in order to demonstrate. Okay, so let's just take them one after the other. So the first one has to do with x plus y is also equal to y plus x. So let's see how that can be done. So first thing you need to take note of while solving this kind of problem that has to do with proving. First, you need to identify the number of variables involved. So in this case, there are two variables involved, because that is going to give you or inform you in order to construct the truth table. Right, so we have two variables x and y, and then recall we said based on the number of variable, the fact of this formula, so you have 2 raised power of 2 because the number of variable is 2, so which is going to give us 4. So in forming the truth table, you are going to have a combination of 4 digits based on the 2 variables. So let's go ahead and construct our truth table for that variables x and y. Right. So we have it this way. So let's begin. We have x, and then we have y, right? So what we need x. So let me clean this so that we can have a perfect representation of excuse me, of the solution. So x, we are going to need x plus y, right, at the third column. So at the fourth column, we are going to create that for the y plus x so that we can compare the solutions, the left hand side and then with the right hand side, right? So remember, 2 raised power of 2, we have 4 input combinations, so we are going to have 4 columns to represent that, right? So let's populate our truth table, starting with the variable x. So you are going to have 2 zeros and then 2 ones based on what we did in the last class. So for the variable y, you populate the table in this form. So it starts in decreasing order, right? And then you have 1. You can also populate this table by taking note of that, okay, this is binary 0, this is binary 1, and then this is binary 2, and then this is binary 3, just like the way we did that in the first class. Right? So this actually will continue based on the number of variables given. So if it were 3 variables, that would be 2 raised power of 3, and then you end up with about 8 combinations. So you're counting 0, 1, 2 all the way till 7, stop at 7, right? So it continues like that. So let's see, we have x plus y already. We have identified the number of variables, so in terms of x, y. So starting with the left hand side of the expression x plus y, so you are dealing with an OR gate now, right? So for the input component, we said that at least one of the input must be 1 for the OR gate, or for an OR gate to be high at the output. So x plus y, we have it, this is 0, so this is going to be 1 because we have at least 1 in the input. So this is going to be 1, this is going to be 1, and then that's it for the left hand side. For the right hand side excuse me, we have y plus x. So y plus x, this is going to be 0 as well, this is going to be 1 this is going to be 1, this is going to be 1 also, this is going to be 1. So a careful observation, you see that this is actually you're having the same excuse me, you're having the same output in terms of x plus y is equivalent to y plus x, right? So that is it about the first excuse me, the first expression at number 9, excuse me, at number 9. So let's look at number 20, which said x y all bracket prime is equal to, or is equivalent to, x prime plus y prime, right? So I'm going to clean this now so that we'll look at the second solution the second, excuse me, example, right? So if you look at okay, let's see number 20. Let me try to copy that. Okay, I've copied that. So let's see, let's enlarge it. So what we are looking at is x y, all bracket prime is equal to individual x excuse me, s prime plus what, y prime. So remember, the first thing you need to look at for is your number of variables. So in this case, still excuse me, we have 2 variables in terms of x and y. So the same formulae, 2 raised power of 2. So we are still going to have 4 input combinations for the respective variables. So let's construct our truth table for the 2 variables, and then consider the outputs based on the given expressions. So we have 4 columns 4 columns in this form. From the first one we have x, and then you have y, right? So okay, let's see. So we'll need xy, then excuse me, we also need x y, all primed, right? Excuse me. And then in the left hand side we are going to need x prime, y prime, and then we all the x prime and then the y prime together. So let's form them and then work them out to see at the end whether it's going to be compared, whether we are going to have the same solution based on what we have at the left hand side to be equivalent to the right hand side. So let's see x prime, column for x prime, we are going to need a column for y prime and then we are going to also need a column for x prime plus y prime, right? Y prime. So let's see, remember we have 2 zeros for the first column in the variable x excuse me, and then for the y you have 0 1, we also have 0 1. So xy, so this is an AND gate between xy. So remember for the AND gate we said all the input must be high, must be 1. So in this case, so xy column, this will be 0, this is going to be 0, this is going to be 0, and then we have all 1 in the last column, so this is going to be 1. So xy all prime, so we are going to invert this excuse me, invert this, and then you invert the 1, you have 0, right? So this what we have in the left hand side, xy all prime. So let's take the inversion for x. So if you do that, you are going to have 1, you are going to have 1, and then you are going to have 0, I'm going to have 0 in this column, right? So for y prime now, let's look at the column for y. So this is 1. If you invert the bits, this is 0, 1 changes to 0 excuse me, 0 changes to 1, and 1 changes to 0, right? So let's add them together, x prime and then y prime column. This is 1. You're going to be excuse me, you're going to have a 1 here, we are having a 1 here, we have a 1 here, and then 0, right? So again, when you compare this with this, you find out that we have the same solution. What is in the right hand side, the same thing in the left hand side, right? So basically that's how it works, as simple as it is. You have to identify the number of variables, and then based on the number of variables you populate your truth table using 2 raised power of n, where n is the number of variables that will determine how your truth table is populated in terms of the zeros and one combinations. So you can try that with the remaining Boolean identities. Try to prove what we have at the right hand side to be equivalent to or equal to what you have at the right hand side. So let's move ahead. So we'll be looking at simplification using these Boolean identities. We are going to be looking at the simplification using Boolean identities, right? So for the solutions, some of the solution we have, so let's look at one of the example that says xy plus x into bracket y plus z plus y into bracket y plus z. So let's see how that can be done. So I'm going to copy it to the board so that I show you how it works. So let's go to the board. I have to clean this. So let's paste this. So given that we are going to simplify this expression using Boolean identities, right? But before we begin, let's let's simplify this using the Boolean identities. Remember, we are given f is equal to x y plus x into bracket y plus y plus plus z, right? You close your bracket, and then you have also plus y into the bracket of y excuse me, plus z. So we're asked to simplify this. So what you need to do is first you will need to open the bracket, right? Involve those ones that have you need to have bracket, expand that first, and then so after the expansion of the bracket, so what you want to do is try to see which of the Boolean identities applies in an attempt to reduce the number of literals or variables as far as the given expression is concerned, right? So let's see how that can be done. So we have x, y again, and then plus so if we open the bracket, we are going to have x, y plus what? X, xz, right? Plus, so this is going to be y dot y. This is Boolean algebra, but if it were the ordinary algebra, we are going to end up with y squared. But remember, we are dealing with Boolean algebra. So if we expand this again, you are going to have y z, right? So now remember one of the laws say when you have x plus x is equivalent to x. So irrespective of the number of terms or literals that are repeated several times, so you are going to maintain 1. So in this case now you can see that x y appears or repeated twice, right? So in this case, based on that Boolean identity, x plus x is equals to x, we are going to maintain xy, right? So xy plus xz, excuse me, xz, and then similarly y dot y, just like one of the laws that said x dot x is equivalent to x. So in this case now we are going to maintain just y, right, based on those Boolean identities. So I have my y plus what? Y and y z. So at least we have started reducing the complexity in an attempt to reduce the Boolean expressions. So excuse me, one of the reasons why we'll have to do the simplification is to reduce the number of variables. By so doing, we might have reduced complexity, we might have reduced cost in terms of the number of gates that are being used. For instance, if you look at the original question given, xy plus x into bracket y plus z plus y into bracket y plus z, you will notice that if we begin to count the number of gates that are operating from the original question, you will see between x and y we have an AND gate, and then we have the OR gate, and then between x into bracket y plus z we also have an AND gate, and then you have an OR gate in between y and z, y plus z, right? So we also have another OR gate here, OR gate, and then between y into bracket y plus z you have an AND gate and then an OR gate. Right? So at the end of the simplification, as you are going to see, we will see that we might have reduced complexity in terms of the number of gates, and then we will make an attempt to draw the circuit diagram. You can see that the complexity might have been reduced. So let's continue with the simplification. So in this instance, you could see what we try to do. We try to factor out those literals that we enable us apply the Boolean identities in order to simplify the circuit. So careful observation, you will see that we can put this together, factor out y is common, and then let's see which of the Boolean identities actually applies to that in order to reduce the logic expressions, right? So we have xz into plus y into the bracket, so y is common, so plus z, right? So we have this plus z. So y plus z, so this is going to be equivalent to what? 1. So if that should be the case, based on one of the Boolean identities, x plus 1 is equal to 1. So we are going to have x y plus what? Plus x z, right? Plus y, because 1 plus z has turned to 1. Right? So we can also compare this with y so that we can factor out y. So if you do that, we are going to have, let me write it clearly so that you could see exactly what we're doing. So if you bring this xy plus y together, right, and then we have x z on the other side. So if let's factor out y, so y is common, so y into the bracket of x plus 1 plus x excuse me, plus xz. Again, you will notice that based on the Boolean identities, this is equivalent to 1. So if that should be the case, our final expressions will be y plus x z. This is going to be, this is our final expression, our final simplified version of the original expressions, right? So let's even make an attempt to draw the circuit diagram of the final expression. So we have 3 variables in terms of x, y, z. So let me make an attempt to draw the circuit diagram for that. So x, y excuse me, z, right? So we have y. So okay, let's try to represent this first, xz, because it is it has the and symbol, it has the art symbol. So let's have it this way, right? So xz, you have xz, this, and then ORing them by y. So this is going to be your xz. Remember, this your xz, right? And then you have your y, a representation of y. So this will now form your y plus what? Plus xz, right? So that's how the simplified circuit actually looks like. Of course, you can make an attempt. So let me leave this as an exercise for you. Try to draw the circuit diagram for the original question. So just follow what we did with the simplified version for the last part of the expression. After the simplification, just what I just did now, follow suit and then try to draw the circuit diagram for the original question. So the number 2 has been left for as exercise for students to try out. Y is equal to a b bar, c plus a bar b c bar plus a b c plus a b bar. First, you need to identify the number of variables. Try to bring the lifetimes, and then see at which point the Boolean identities might apply, right? So let's go ahead. Let's look at